I've had some requests to look at a more complicated problem that ties a bunch of these week's discussions together. So what if, for example, we had some collision from Unit 5 that led to some sort of conservation of energy problem from Unit 4 that led to some projectile motion problem from Unit 2? How could we tie all of these things together? What are things that we have to hold constant? What are things that have to change? And how can we look at these different scenarios? And so to look at this, I'd like to look at a specific type of problem that ties a lot of these things together. Now, the problem that I'm proposing is one much like the one that's set up here. In this problem, we have a red mass, m1, initially moving on at some speed, v1 initial. It is then going to hit a second mass, the blue mass here, m2, and after the collision, that blue m2 mass is going to be moving at some v2 final. Now, after the collision, that blue ball is going to continue on to do other things. It's going to go up some ramp, where we're going to have some conservation of energy, and then it will leave the ramp and go through some projectile motion. So it's leaving the ramp from some height at some angle of inclination, and it's going to hit the ground some distance d away from the edge of the ramp. Now this is just the setup for some problems, and I'd like to look at this problem in a couple of different ways to illustrate how different parts of a problem can tie together. And before we really get into it, I wanted to highlight something about these collisions. So let's say we had the collision as it is shown here. There's really two scenarios that we could look at. We could look at the case of a perfectly elastic collision. And in a perfectly elastic collision, we know that the total energy of the system is conserved as well as the momentum. What you should have is these equations written down on your sheet as you're getting ready for the exam, because what we know in a perfectly elastic collision is that the velocity of v1 after the collision is m1 minus m2 over m1 plus m2 v1 initial plus 2 m2 over m1 plus m2 v2 initial. And we also know that v2 final is equal to 2 m1 over m1 plus m2 v1 initial. And we have m2 minus m1 over m1 plus m2 v2 initial. So these equations are going to hold and allow us to find what the speed of each of these balls is after the collision. Now, just for argument's sake, let's say that mass 1 is smaller than mass 2. And for numbers' sake, maybe we say that m1 is 5 kilograms and m2 is 8 kilograms. This is something that's perfectly and totally allowed. Well, then we could come up with some numbers. Maybe, for example, we wanted to find out after the collision, how fast is m1 moving? So here, if we start with a situation where v2 isn't moving before the collision, for each of these scenarios we can remove this. If I wanted to find v1 final, it would be m1 minus m2, in this case 5 minus 8 over 5 plus 8 v1 initial, which is going to be what? 5 minus 8 is minus 3 over 13. So it's something like negative 1/4. I could pull up a calculator here, I suppose. And here with our calculator, 5 minus 8 divided by 5 plus 8. Yeah, it's a minus 1/4, minus 0.231. v1 initial. So this is a scenario where the first ball, the 5 kilogram mass ball, hits the second ball and bounces backwards. Okay, this is one extreme case. Obviously, once we know this, then V2 final is going to be 2 times 5 over 5 plus 8 V1 initial. This is what, 10 divided by 13? So we can clear everything here. 10 divided by 13. So it's positive 0.769 V1 initial. So after the collision, the first mass is going to bounce backwards, the second mass is going to go forward and progress with the rest of the problem. Now this is one extreme scenario. The other extreme of the scenario is perfectly inelastic. And with a perfectly inelastic collision, we remember that M1 is going to hit M2, and the two objects become one object. So M1 V1 initial is going to be equal to M1 plus M2, this combination moving at some final speed, right? And so this scenario, if we wanted to find out how fast M1 obviously in combination with M2, but all of that mass from M1, we wanted to figure out how it was moving. V final is M1 over M1 plus M2 V1 initial. And we can get out our calculator again. 5 divided by 5 plus 8. So we see that it's 0.385. V1 initial. So I wanted to highlight these two cases in particular. Because from this, we see something kind of interesting. I could have that first red mass, M1, coming in, and it could have a collision where after the collision it is bounced backwards. We could have it come in and become a new mass with M2 and be moving forwards. For any other collision that doesn't have the word perfectly in it, the speed of M1 after the collision can be anything in between these two values. Anything in between these two values. So this is bouncing backwards, this is continuing to go forwards. There is nothing that says that I couldn't just arbitrarily say that V1 after the collision is equal to 0. 0 is greater than this, 0 is less than this. Clearly, for any value of V1 initial. So as I do this problem initially, I'm going to say that the speed of V1 after the collision is 0. This is not going to have conserved energy. This is not a perfectly elastic collision, but neither is it a perfectly inelastic collision. This is an allowed collision that's somewhere between these two extremes. Okay? Now let's say this is the case. I can have some collision where M1 comes in and stops. That's something that's perfectly allowed. Let's pull up our picture again. If that's the case, what are some things that we know? We know initially that there is a collision and an equation that's associated with that collision. So we start with M1 V1 initial worth of momentum. After the collision, we only have M2 moving at V2 final. That's all we've got. So this is the equation that explains everything that happens with the collision. What happens next? Well, now M2, not connected to M1, because this was not a perfectly inelastic collision, is going to go up some ramp. So what do we have going on then? Conservation of energy. And what do we know about conservation of energy? I know that the kinetic energy of M2 at the bottom of the ramp is going to be equal to the kinetic energy of M2 at the top of the ramp. I'll just say that that launch speed is V, just to make things easy. But we also have potential energy here. So this is a statement of conservation of energy. Well, now the ball, M2, is sitting at the top of the ramp, but it's going to go through projectile motion. So what do we know about the projectile motion? Well, I know that for the projectile motion, in the horizontal direction, we see that D is equal to V cosine of theta t, and in the vertical direction, 0 is equal to H plus V sine theta t minus 1/2 G t squared. This is everything that's going on in the problem. Okay, well, we've already said we're looking at a case where M1, we can call it 5 kilograms. M2 is 8 kilograms. Okay, well, let's just set theta equal to 30 degrees. Okay, that's fine. And while I could give you lots of things, why don't I say that H is 0.5 meters and D is 1.5 meters? This is perfectly fine. So given this picture, I can certainly give you D, and I can give you H, I can give you theta, I can give you M1 and M2. And from this set of information, it turns out that if you wanted to, you could calculate V1 initial that is required to make this happen. How do I know this? Because there are 4 things that we don't know, and we have 4 equations that are unique. So what are the things that I don't know? Here I know H, I know theta, I know G, but I don't know T and I don't know V. In this equation, I don't know V and I don't know T, but I do know D and cosine theta. So from these 2 equations, I can get T and V. From V, I can plug that in up here, and I know H, G, M2, M2, M2. If I use this V and plug it in, I could use this to find V2 final. And if I know V2 final, now I know V2 final, M2, M1, I could use this to find V1 initial. My unknowns are T, V, V2 final, and V1 initial. 4 equations, 4 unknowns. So what are the values of this? Normally what I would do is solve this for T. From this first equation, T is equal to D over V cosine theta. Now I can take that horizontal equation and put it into the vertical equation. It says that 0 is equal to H plus V sine theta over V cosine theta is just tangent theta minus GT squared, which is G D squared over 2 V squared cosine squared theta. So from this equation, I know H, D, theta, G, everything I know in here, I know except for V. So I can solve this uniquely for V. And here we see that G, D squared over 2v squared cosine squared theta is equal to h plus d tangent of theta. Rearranging some terms, v is going to be g d squared over 2 h plus d tangent of theta cosine squared theta, all under a square root. Here you can kind of see what all of that is. I can take this v and plug it in up here. From here I see that 1/2 m2 v squared is equal to 1/2 m2 v2 final squared. Actually, I want to know v2 final, so never mind. So 1/2 m2 v2 final squared is equal to 1/2 m2 v squared plus m2 gh. I can multiply everything by 2, divide everything by m2, and find that v2 final is equal to v squared plus 2gh under square root. Now I know what this is. I can plug that in up here, and this tells me v1 final is m2 over m1 v2 final. So I can work my way through this progression. Now let's pull out a calculator and see what we can get from this. Let's clear everything, show you the calculator. So I've got, let's do the inside here first. So 30, the tangent of 30 times d is this. I need to add h, which is 1/2, multiplied by 2, multiplied by cosine of 30 squared, is equal to this. Put that in the denominator, times 9.8 and times 1.5 squared. So this is some number. I take the square root. Here we found essentially that v was 3.28 meters per second. That is how fast the ball m2 had to leave the ramp in order to have the value of d that we had before. Knowing v, I can plug that in here. Let's square this, plus 2 times 9.8 times 0.5 is equal to this. Take the square root. So 4.53 meters per second. And now knowing this, we can go back to this equation. I can multiply this times 8, divide by 5, and I've got 7.26 meters per second. So we see from this that I can solve this system of equations. I've got a collision, I've got conservation of energy, I've got projectile motion. Each of these things tells me a little bit of the problem, but now I just need to solve for the unknowns. Here I don't care about the time. The time could be interesting, I suppose. It is technically another unknown, and we could find it. Because I know v, I could put that in here, and we could find out what the time in the air was if we cared. Okay? Now, let's say we know all of this stuff. What if we decided to change the collision? What if v1 initial really is 7.26 meters per second? But now I don't want the collision as proposed. I want to have a perfectly elastic collision. What would change in the problem? Well, v2 final would be different, because v2 final would be different. it would be moving at a different v at the top of the ramp, and because it's moving at a different v at the top of the ramp, it would have to have a different range d. So d is going to have to change if we change the collision type. And I'm kind of curious what else changes. So again, we can go back to this problem. And if instead we were told what v1 initial was, what changes? We're going to have a perfectly elastic collision now. Which is also allowed. And this tells me that v2 final is going to be equal to 2m1 over m1 plus m2 v1 initial. So if you gave me what v1 initial was, I'll tell you what v2 final is. But from here, we also have conservation of energy. Once again, 1/2 m2 v2 final squared is equal to 1/2 m2 v squared plus m2 gh. So if I know v2 final, I could plug it in here and find out what v at the top of the ramp is. Notice here that v is going to be v2 final squared minus 2gh. That's going to be the speed at the top of the ramp. Now it goes into projectile motion again, right? What's changed about projectile motion? Well, I know that in the horizontal direction, d is equal to v cosine theta t, and that 0 is equal to h plus v sine theta t minus 1/2 g t squared. This is the same equation we had before. This is the same equation that we had before. This is the same equation that we had before. Nothing has changed. In fact, if we wanted to, what we're probably going to do is find v2 and plug it in here. That gives us v. Once we know v, we can plug it in here. Once we know that, we know h, we know v, we know sine theta, we know g. We can solve for everything except for t, right? So from this, we could find time. We could take that time, plug it in here. We already know what v is. We could find out what d is. Perfectly and totally allowable. This is, once again, a quadratic equation that we have to solve, right? So we could go through this whole process and solve this again. We run through the numbers and we would find a different value. So just to highlight how this is really done, I'd like to take a step over to Mathematica and show you how very quickly, rather than using a calculator, what is really going on in the process. Because all we're doing is solving a system of equations. So let's go to Mathematica here. So in this problem, I have got I want to solve a system of equations. And initially, when we did this, what equations was I trying to solve? Well, we had a collision where initially we had a mass m1 moving at v1 initial. And after the collision, we only had m2 moving at v2 final. I happen to know what m1 and m2 and v2 final are going to be, or whatever that is. But this was our collision in our first case that we've already run numbers for. What else do we know? Conservation of energy. 1/2 m2 v2 final squared is equal to 1/2 m2 v squared plus m2 g h. So that was conservation of energy. That's what it is. What happened next? Well, we had projectile motion, right? So projectile motion, we were told that d is equal to v cosine of, theta times t, and that 0 is equal to h plus V sine of theta t minus 1/2 gt squared. These were the equations that we had. Now I'd like to solve this for the four unknowns. What four unknowns do we have? We had t, we had v, we had v2 final, and we had v1 initial. Now, just for argument's sake, we're looking at a special case, and we have some assumptions. First of all, I want a t that is positive. There's actually two t's that are going to work, but I want the one that's greater than 0. I want the velocity that's greater than 0. I want a v2f that's greater than 0. And I want a v1 initial that's greater than 0. We could turn the whole problem around. We could change all of the signs, and everything would still totally work. So now I just need to tell what were the details of our problem. I want g equal to 9.8 because that's what I used. M1 was equal to 5. M2 was equal to 8. Theta is equal to 30 degrees. And I'm going to make sure I get all these. It's not comma, that is there. And we had h was equal to 0.5 and d was equal to 1.5. So let's solve this. And it crapped out somewhere. I'm not sure what the problem is. Oh, I have the wrong bracket here. Has to be like that. Has to be like that. Okay, there it works. Now notice here, we get a couple of numbers that we have seen before. So if you go back in the video, we found out that v was 3.28 meters per second, that v2 was 4.53 meters per second, that v1 initial was 7.26 meters per second. Mathematica agrees with us. Now what changes when we change our collision? We can do all of this exact same stuff. So I'm going to start a new kernel just because it's remembering what all those variables are. But we're doing something very similar. So let's copy this, paste it here. We're essentially doing the same problem now. But what's different? I'm not going to give you d. I am going to tell you in advance what v1 initial is. And we're going to say that v1 initial is 7.2551. Okay? Now that's as far as things that we know. What has changed here? Well, we just have a different type of collision. In this new collision, we are told that v2 final is equal to 2 m1 over m1 plus m2 times v1 initial. Has anything else changed? Nope. Conservation of energy is still exactly the same as it was before. Well, what about the projectile motion problem? Projectile motion problem, exactly like it was before. We might have a different progression of what we're finding. So now, for example, we might want the answers here in a different order. I'm giving what v1 initial is, so maybe next I want to know what v2 final is. And after that, I want to know what v is. And after that, I want to know what time in the air is. And after that, I want to know what d is. This is what I was calculating, and this was the progression that I laid out on the page. When we're doing this problem, we'll first find what v2 final is, then we'll find out what v is, then we'll find out from the quadratic formula what the time is, and then we'll find out what the value of d is going to be. And just as we had before, we're going to set up our assumptions in such a way that v2 final is positive, v is positive, t is positive, and d is positive. Okay, well, what do we find now? Things are different than they were before. In this perfectly elastic collision, it turns out that V2 final is different than it was before. It's now going faster after the collision. Perfectly elastic. We don't have any energy that's lost to heat, no energy lost to sound, no energy lost to denting, no energy is lost. So M2 is now allowed to move a little bit faster after the collision. And we see that with this V2 final. Because it's moving faster after the collision, it's also moving faster at the top of the ramp than it was before. Because it's moving faster at the top of the ramp, it's in the air longer than it was before. Because it's in the air longer than it was before and moving faster, d is bigger than it was before. Remember, initially, d was 1.5, and we figured out what initial velocity for that particular type of collision would make that work. We change the collision type and try to progress it forward, and we get a different number for d. Now, what I wanted to highlight with this is really all I changed was a system of things that was given to me, and I changed a collision type. That's it. All of the other stuff was the same. And so when you're thinking about what it means to put together a complicated problem like this is what you should be thinking about. I'm coming up with parts of the relationship. Some of those things are what they are. A projectile motion problem always kind of looks in this particular way. And conservation of energy always looks this particular way. And then we have this collision-y type thing that's happening in a particular way. And depending upon what's given to me in the problem, I could progress forward. What's given in the problem might require me to progress back to find things. But all we're really doing is solving systems of equations. Those equations come about from the physics that we've learned about. So in this problem, we tied together projectile motion. We tied together conservation of energy. We tied together a collision. And what you'll notice is that the solution to doing this was just solving those relations. That's what we were doing. That's it. And so, if you're trying to get ready for an exam, based upon topics like this is what you need to keep in the back of your mind. Very often the problem is going to be posed in such a way as I'm given this picture and there's no numbers or anything on it. I need to figure out what the progression of stuff is based upon things that are given to me. We've just done one problem two different ways. One of them I gave you details about the projectile motion. One of them I gave you details about the collision. Or what the initial speed of the first ball was. The different kinds of collisions and stuff, but they progress in different ways. You solve them in slightly different ways, but it's still a solution to a system of equations. That's all it is. So part of the problem is going to be talking about, okay, well, what is the collision? What does conservation of momentum look like? And part of it's going to be the energetics. What does conservation of energy look like? Part of it might be related to, in this particular case, the projectile motion. What's projectile motion look like? Those are the equations. That's all of the physics of the problem. Everything else is math associated with solving that system of equations. The physics is those little parts that give you the equations. That's what's really going on. That is often something that is missed by a lot of students that are learning physics for the first time. They don't recognize that really the physics is not working with these individual numbers. The physics isn't even really solving those differential numbers. What we're looking for is the connections between these different parts of the problems. And that's all done with variables. And maybe you could put numbers into it eventually, but if you plug something wrong into your calculator, I'm not grading on arithmetic, maybe a little bit, but not really. What I want to do is give you credit for recognizing the important parts of the problem. What does conservation of energy look like? What does the conservation of momentum look like? What does projectile motion look like? That's the important stuff. When it comes to forces, you can have all kinds of other things as well. And now, as the semester rolls on, we're going to get into rolling problems. So how does rolling get incorporated into this? Are we going to allow balls to slide without friction? Or are they going to roll without slipping? Those two situations are completely and totally different. And then we can get into other kinds of problems as we move in a little bit later in the next chapter into universal gravitation. What if I did this exact same problem on a different planet? What's the same and what's different as we change the acceleration due to gravity, for example? Or we can get into fluid dynamic problems. We can figure out, how does a swimming pool change its pressure as a function of depth if we were to put it on the moon instead of having it on Earth? Or put it on Mars instead of having it on Earth? What's the same? What's different? How do we talk about those different things? Because it's all associated with the variables. It's associated with these simple principles of kinematics, force, energy, momentum. They're going to be tied over and over again. So I hope that this demonstration was illustrative of how these connections are really supposed to work and how you can prioritize focusing on the individual physics parts of the problem so that if maybe something happens in your calculator, you can still get a lot of credit.